Another one is the analog filter specification. So in this we are considering omega versus, that is a gain, omega in radians per second, and gain in decibel. So for converting into a decibel scale only, here everything just the same thing we are converting into a decibel scale. So here we are considering the normalized value 1. So another gain is a del P, another one is a del S. So corresponding will be omega P and omega C. So it is a passband edge frequency, passband stop frequency. So in between we'll get it is a cutoff frequency which will occurs exactly at -3 decibel from the maximum value. So if you are converting everything into a decibel scale, so 20 log of 1 will be 0 decibel, 20 log of 1 minus del P we are considering it is a Kp. So the Kp is nothing but it is a AP. AP is passband attenuation. And similarly here it is 20 log of 1 by root 2 is it is -3 decibel, and 20 log of del S we are taking it is a Ks. So Ks is nothing but it is a AS. AS is a stop band attenuation. So this exactly everything we are converting into it is a decibel scale, and the mathematical description of the frequency response we are taking from omega value from 0 to omega p. From 0 to omega p if we are considering only this we are achieving. So we'll get 1 minus del p 2, it is a 1. So again if you are considering omega is greater than it is omega s if you are considering, so only this is we are getting is del s. So this is the mathematical description of frequency response, and if you are converting into decibel scale, the Kp is 20 log of it is 1 minus del P. So that value Kp is nothing but it is AP. So when it is omega is equal to this 1 minus del P is omega value will be equal to your omega P, and Ks is nothing but it is 20 log of it is del S. So it is a stop band ripple in decibel. So that is As will be equal to Ks when is the stop band, that is omega is equal to it is a omega S. So this is the your Butterworth characteristics curve. So this is your ideal characteristics for the low pass filter. Up to cutoff frequency it will passes all the frequency. After the cutoff frequency it will stop the frequency. So this is your ideal characteristics. So we cannot achieve this infinite slope in practical case. So we are approximating. So we are getting the curve will be like this. So this is your Butterworth curve. So now here this is the characteristics magnitude frequency response that can be find out by h of j omega equal to 1 divided by 1 plus omega divided by omega c to the power of 2n, the whole power of it is 1 by 2. So in that n if you are taking, n is nothing but your order of the filter. So from this figure we'll come to know that when the order is goes on it is increasing, n equal to 2, n equal to 10, n equal to 12. So the 12 the curve it is coming like this, a green, correct? So this is coming very closer to your ideal characteristics. So whenever the order is goes on increasing, so your ideal it will reaches to your ideal characteristics. So always you have to take a higher value of n, then it will come closer to your ideal characteristics. So your n is the order of the filter and omega c is the cutoff frequency. So here magnitude square function if you are taking, so just we are squaring this function, so this 2 and 1 by 2 will get cancelled, so we'll get this expression here. So in this expression if you are designing for normalized Butterworth filter, we have to consider omega c value will be equal to 1. So if you are substituting omega c as a 1, so here we'll get the expression 1 divided by 1 plus omega to the power of 2 into n. Another one, so we have to find the order n, so we have to use this formula, any one of the formula, and we can find out. If we are using this formula, so it is log of it is 10 to the power of 0.1 as, here it is minus 1 divided by 10 to the power of 0.1 ap, and then minus 1 divided by 2 into log of omega s by omega p. So here as is nothing but stop band attenuation, ap is nothing but pass band attenuation. This everything should be in decibel, and here it is omega s is stop band edge frequency, omega p is pass band edge frequency. So this will be in radian per second. So we can use this formula, or if you are squaring here all the term, so here this will come square root of this one. So this we can write log of omega s by omega p, the whole power of 1 by 2. So here the squaring and this 1 by 2 get cancelled, so we'll get the term log of omega s by omega. So we can use this formula or this formula, and one more formula also we can use. Instead of as, here if you are substituting ap by AS. So here also we have to substitute by omega P by omega S. If you're using also, we'll get the same value only. So we can use any one of the formula. So here AP and AS will be in decibel and omega P, omega S in radian per second. So next one is we have to find out the cutoff frequency. So sometimes in question they will ask to meet the pass band than the stop band. So we have to use this formula omega C equal to omega P divided by 10 to the power of 0.1 AP minus 1 the whole power of 1 by 2 1. So if they are asking stop band requirement than the pass band, then we have to use here it is a stop band omega S divided by, here also we have to substitute it is a stop band attenuation, or we can use the arithmetic mean of this too. So normally they will not mention in the question which requirement you have to use. If they are not mentioning anything, so you can use only this formula and we can find out. No need to worry about this remaining two. So this is the thing we have to remember. One is your magnitude of the frequency characteristics of the Butterworth filter. Second one, what is the order, that formula we have to remember. And third one is the cutoff frequency. So this, if they are not mentioning anything, you can use this formula alone and we can find out.